putting together. And so I can see that this one is a vapor pressure in the, as far as A is concerned. And if you're looking at, this is a 1 minus xb, so therefore, actually this plot, this side. Okay. So this is this partial pressure, and that's the one is essentially this way. And that's a partial pressure of a B. Just what you see is just a linear dependence on composition with respect to their own mole fraction. So just by doing this, you can get these two, and then what we know, the pressure, total pressure, is a PA plus PB. Those are what's happening in the total pressure. So what's my total pressure here? This versus this purple line plus white line, right? And we'll see naturally coming this way. So this is your P, which is a summation of PA plus PB. This is actually too good story to be true, okay? But this for particular case of toluene and benzene, it doesn't deviate too much from this kind of scenario. This is a very, very nice scenario. Why? Because whatever happening in the gas phase, I have a predictive knowledge is what I can get from the liquid phase. Right? This is an information that I extract from the liquid, pure liquid, composition in the liquid, and I can predict what's happening in the vapor phase. That should be true, and if that's happening throughout this whole entire composition one, this will be nice. Okay? And the way that how people see is I'm going to highlight what is a real data here. The real data is actually this one. This is a real data. This is essentially the total vapor pressure that you feel, and by changing the composition, it kind of nicely follows the chemical composition. Okay, so now I am going to that's number 3. Example 2, which is more likely the real example. The example here is essentially acetone CS2. This is a carbon disulfide with an acetone. Okay, those are the liquid. They are fully miscible. And then, so I'm going to compare this. Okay, let me draw these two diagrams. What I said before was a pressure, total pressure. This is 0 x 1. Right? And so this is what linear dependence, and then I can kind of see that that will be a partial pressure of A star, and that's a contribution from there. And then this is a contribution from the PB, and this is a case for when you are mixing the benzene with something that looks like very similar, toluene, right? But when you have an acetone, CH3CO CH3, and carbon disulfide. Actually, most of the case, this is an example, and then this one. Zero. So here is this is toluene. Here XC CS2, carbon disulfide. And this is a vapor pressure of carbon disulfide. So this means they are more volatile compared to acetone. And if you do that, that's what the data looks like. Okay. So this is a one for vapor pressure. Whereas this is a one looks like some complex curve. And I like to draw this something as a baseline here. Okay? And this is more popular and more common. This is what is not so common. And this is an ideal solution. I guess if you want to call it, this is a non-ideal solution. And do I have a predictive knowledge on how this curve looks like? The answer is no. Okay? I don't have any prediction of knowledges. So yeah, it works for certain cases. It doesn't work for most of the cases. Right? So why do I even learn the Rao's law? Probably you heard about Rao's law in your general chemistry class. Right? We said Rao's law because it works. Okay, it works right here only. Okay, if I zoom it out, okay, it's more like this. Okay, and then I'm going to use so here, so let me just focus on the one component, which is a PA, which is the following XA PA star, right? Because throughout the entire ranges of composition, they have a very nice relationship. They have a non-monotonic kind of curve relationship. But when you're looking at here, so I can really plot what is called the vapor pressure for PA, which is a carbon sulfide, right? This dotted line still, I'm just using XA times PA star as my guideline. Okay, I don't have a nice red one. When you have no CS2, you should start from here. That's for sure. Okay. When you have 100% A, you should have ended up here. So the starting point, end point is the same. But what's the component of PA, which is a partial vapor pressure on this, is more like this. Okay, it's not linear relationship. So the ideal solution law fails miserably. Fails. Not good. I keep on telling you it's not good, except tiny little region here. If you look at that, oh, this is not so bad, right? This is good actually. So therefore, PA is XA times PA star. I can still using it as long as XA is close to 1. Right? But if XA is like a 0.5, I cannot use this law. And we have no means to kind of predicting what's this vapor pressure contribution, even the total pressure contribution. Okay? Make sense? Yeah? So it's now, so now let's take a little step back. This is not in the textbook, but I can explain it to you a little bit here. So let's look at the scenario you had before. So I'm on A, surrounding B. Okay, and I draw this molecule near to each other because they are in the liquid phase, right? Okay, the liquid phase. And if this molecule A likes to be bounce to the vapor phase, and there are interactions. So this is what used to be the energy of AA contact and energy of BB contact and the energy of AB contact. So essentially the contact energy is changing before you have this pure AA contact. Now you're enforcing this AB contact because of new contact that's happening here. And I'm hoping this AB interaction is same as an AA interaction or BB interaction. Do you know how unrealistic it is? Right? I'm a liquid. Benzene have an interaction. Toluene has an interaction. Benzene, toluene, they have the same attraction. No, right? But they are not so different, right? So having said that, I was lucky. I was lucky to have this kind of scenario because this scenario versus, so now you have an A, let's just focus on the A. In the higher composition, this is, I'm going to just say different composition. So this is now you enrich your B, and if A, the tendency for them to escape, now if they have the same interaction, it doesn't matter how much of the B versus A is surrounded by, and they follow the ideal solution. But now the real solution is the following. In the most cases, in all cases essentially, this is not a favorable. They are angry, okay? They don't like each other. So it's almost like they don't like it. So therefore they're gonna push this one to the gas phase more. So that's why this is a pressure that you're supposed to have. Everything is the same interaction, AB contact, but now you have an additional enrichment of A compared to what is predicted by Raoult's law, right? If it is a 50-50, and then if you guys A and B, okay, there is a person with an A last name and a person with a B last name. If you guys don't like each other, you want to throw the person out from here, and this is happening more likely happen. So therefore, this is what PA. The composition is actually what is predicted by ideal gas law, which is just a mere composition dependent on what is supposed to happen. Okay? So that's why you are seeing this positive contribution or positive deviation. But this one still works because in the limit of, actually this is a scenario. Here I only draw only a 1B here, right? This is a case where corresponding to this one, just having a few would not disturb this kind of obedience not much. So therefore I can use this relationship. So once again, the beauty of this Raoult's law is connecting the bridges. This is a property of liquid or gas. This is what's happening in the bottom, right? This is what's happening. This is what defines your liquid properties, right? And then the vapor pressure PA, which is this is in the gas phase. They're making a bridges in between these two.